Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. In today's lecture, we'll continue discussing more on the stability properties of LTI systems and how exactly they are related to the eigenvalues. So just a quick reminder, in the previous lecture, we talked about Jordan blocks. Now Jordan blocks have a huge role to play in the stability. Let us see how. So in the previous lecture, we discussed in detail about Jordan matrices and how they relate to a given square matrix A. Now, so the spectral decomposition theorem tells us how exactly the relation goes. So it says that there always exists a matrix J such that any matrix, any square matrix A can actually be decomposed as Sj S inverse, where J is a Jordan matrix and S is a matrix which is constructed using the eigenvectors of A such that every column of S is one of the eigenvectors of the original matrix A. Now, as time progresses, let us say we are looking at what happens to the system when time tends to infinity. In that case, we see that the only parameter that depends here on time is the matrix A. Now, substituting the spectral decomposition theorem here, using it here, we see that we can write it as the product of Sj S inverse k number of times. And what we see here is that here repeatedly we get this formulation of S into S inverse, which becomes identity. Similarly, here we will get identity, here we will get identity. So what actually remains is the first S that we have from here, then J gets multiplied to this J, which keeps on getting multiplied to the subsequent J's. And how many times does J occur here? K number of times, giving us the following result, that limit k tends to infinity x of k is actually equal to S times the limiting behavior of J to the power k times S inverse times x0. Meaning that now, instead of looking at the matrix A, we need to look at the limiting properties of the matrix J and see what exactly it looks like. And we already know that Jordan matrices actually have some nice forms. To quickly remind you of some results, now a matrix A is called as a semi-convergent matrix if limit k tends to infinity J to the power k exists. And in the special case, when this limit goes to 0, we call that matrix a convergent matrix as given here. So now the question is, how do we analyze if the J that is given to us, whether it is convergent, whether it is semi-convergent, or is it neither, meaning if it diverges. So let's see how do we answer that question. Okay. Now to answer that question, let us recap what we discussed in the previous lecture, which is that any Jordan matrix can actually be represented in the form that is given here, where each Jordan block is actually associated with an eigenvalue. Sometimes a given eigenvalue lambda can actually have multiple Jordan blocks which is associated with it, meaning the geometric multiplicity of lambda is actually greater than 1. Okay. Now, in order to of course analyze J to the power k, we will need to analyze what happens to J1 to the power k, J2 to the power k, and so on. Now, let us start with the simple case of when an eigenvalue is simple or semi-simple. So then we know that every Jordan block is of size 1, meaning Ji can simply be written like this, which means that for semi-convergence to happen, meaning the limit only has to exist and not necessarily go to 0. In that case, we know that when lambda I is equal to 1, then this limit exists. For the Jordan block to be convergent, we need lambda I less than 1. Why? Because now when we take the limit of Ji to the power k, if the lambda is less than 1, we know that it goes to 0, which is the definition or the requirement for a matrix to become semi-convergent. So note that a matrix which is semi-convergent the other way around, a matrix which is convergent is also semi-convergent, but vice versa may not be true. Okay. So we discuss what happens when we have an eigenvalue which is simple or semi-simple, then every Jordan block is of size 1. But let us now move to the case when we have an eigenvalue for which the algebraic multiplicity is actually not equal to the geometric multiplicity. In such cases, we know that the particular matrix becomes a defective matrix, meaning we won't be able to find enough number of linearly independent eigenvectors to do the Jordan decomposition, and we have to look for generalized eigenvectors. Okay. So then we know that in those cases, the Jordan blocks takes this very interesting form, where along the diagonals we have all the eigenvalue, and the super diagonal now has entries equal to 1. So what happens in this case? When can we say this such a JI, such a Jordan block is going to be semi-convergent or convergent? Meaning, if now we take what is going to be its value. To do that, let us write up the expression of what Ji raised to the power k looks like, and after some algebra we can see that it takes this form. Now let me point some interesting things here. So if we see this, if we look at the coefficients of the terms that are here, we see that all of these coefficients are dependent on the time parameter k, meaning as time keeps growing, the value of the coefficient keeps on growing, each of these coefficients, right, which means that this term keeps on growing unboundedly, right. So now what happens when lambda I is equal to 1? We see that in such a case all of these terms will be equal to 1, but the coefficient here, each of these coefficients actually keep growing, meaning the system will be neither convergent nor semi-convergent. When will the system be semi-convergent? Only when, to counter the increase of the coefficients, the adjoining terms here, if they start to reduce, and that will only happen when every lambda I is less than 1, which brings us to the following results. Let's start with the first result. If we have a Jordan block of size equal to 1, then the results are very easy to imagine. The matrix becomes convergent if and only if the value of every lambda I is strictly less than 1. It becomes semi-convergent if lambda I is less than 1 or it is equal to 1. So please note that we have repeated the condition mod of lambda I less than 1 only to account for this, that every convergent matrix is trivially semi-convergent. While the vice versa is not true. Okay. What happens when we now start to increase the size of the Jordan blocks, meaning we now make the matrix defective? In that case, the matrix is actually convergent and semi-convergent only when mod of lambda I is less than 1. So this is very different from what we get for Jordan blocks of size equal to 1. There, for mod of lambda I equal to, when lambda I is equal to 1, then we can get stability, but here that cannot happen. Please note this important difference for the case of defective matrices. Okay. Now just to remind you, so we have these nice results. We are now able to tell based on the eigenvalue whether or not the Jordan block is convergent or semi-convergent. It is, in general, if the Jordan block is of size greater than 1, it is semi-convergent or convergent only when mod of lambda I is strictly less than 1. Okay. How does this translate to our original system? Meaning, we had the system which we later rewrote in this form. So, now if we have certain convergence properties on j of j raised to the power k, how does it translate to the matrix A, the original matrix? And this is what it looks like. The matrix A is convergent if and only if the spectral radius is less than 1. What is the spectral radius? It is simply the maximum norm of all of the eigenvalues. Now, since the eigenvalues of j and A are the same, whatever makes j convergent or semi-convergent, the same holds for A as well. Meaning, we know that the matrix A is convergent when the spectral radius is less than 1, and it is semi-convergent and not convergent. That is, as is given here, this limit exists and is different from 0. So, this happens if and only if, first of all, 1 is an eigenvalue or 1 is a semi-simple eigenvalue, and all other eigenvalues actually have magnitudes less than 1. So, this brings us to a conclusion on when is a system stable or unstable. Everything, as we can see, depends on the eigenvalues of the matrix A. Let us conclude, let us summarize the results. So, again we start with a discrete time linear system modeled using this equation, which is x of k plus 1 is equal to A times x of k. For convergence, all of the eigenvalues of A must lie within a unit disk centered at the origin, which looks something like this. So, this radius here is equal to 1, and all of the roots which actually lie inside will make the system stable. But now, if we have a system where we have a root which lies outside, then the system becomes unstable. Note that only one root outside of it is enough to make the system unstable, because the solutions will diverge along this. And this is something that a lot of you are already familiar with, I assume, the case of continuous time linear systems, which is x dot equals A times x of t. In this case, as we already know, for convergence, all the eigenvalues of A must be strictly negative, as depicted in this image. Same as before, we need, for stability, we need all of the eigenvalues to lie in the left half of this plane. And if we have even one eigenvalue which now lies in the right half, we know that the system becomes unstable. Okay. So, suppose we have a very large system. Now, for smaller systems, it is very easy to do the computation of the eigenvalues, but for very large systems, it is not always very easy to do that, or it can be computationally not so efficient for some reason, depending on the resources available. So, in those cases, are there any other nice ways using which we actually would not have to solve the characteristic equation, but we can still get some idea on where the eigenvalues of a matrix A are located? So, this question can be answered using the Gers-Corin disk theorem. So, let us see how does the Gers-Corin theorem go. It says that let us start with any square matrix A of size n cross n, which is real valued, and the spectrum of A is simply the union of n number of disks, where each disk is given by this. Now, in order to explain this, let me write out the A matrix, which can now take these forms. and the last entry being ANN. Then the Kerr-Scorin discs are constructed in the following manner. So, the Kerr-Scorin disk is associated with each row of the matrix. Let us take the first row. Then the Kerr-Scorin disk is simply a disk which is centered at A11, meaning the first disk takes this form where the radius of the disk is simply equal to the summation of all of the absolute values of the off diagonal entries in that row, meaning it goes from j equals 2 to n. Now, what does it look like is this. We can mark A11 anywhere, which becomes the radius of the disk, the center of the disk, and the radius, suppose this is equal to the radius, let us call it R1 associated with the first Kerr-Scorin disk, then it looks like this. Now, the eigenvalue, one of the eigenvalues, Kerr-Scorin disk theorem says that at least one of the eigenvalues has to lie inside this disk. So, now we know the location of one of the eigenvalues. Now, using the second row, similarly we can construct yet another disk which is now centered at the diagonal entry A22 and has a radius equal to the sum of the absolute values of all of the off diagonal entries in that row, meaning the center for the second one is equal to A22 and its radius R2 is simply equal to the summation of this, where this is R2. Now, again, one of the eigenvalues has to lie inside of this disk. In a similar manner, we can construct a disk corresponding to each of the rows of the matrix A, meaning it gives rise to n number of disks, and the entire spectrum can simply lie now in the union of all these disks. So, let me just draw a few more disks here. Now, the union of each and every one of them is where the spectrum lies. So, let us see an example to understand this a bit better. Suppose we consider a discrete time LTI system which consists of three interacting individuals who update their states given by the vector x using the update rule being equal to x of k plus 1 is equal to a times x of k. Now, the A matrix for the system takes this particular form. So, of course, while this is a very simple matrix which is of size 3 cross 3, here we can easily go and calculate the eigenvalues. But let us now see, suppose we do not go about that route of calculating the eigenvalues using the characteristic polynomial, can we in any way actually comment on the location of these eigenvalues? And yes, we can do that using the Kerr-Scorin disk theorem. So, let us now construct the disks associated with this matrix, and they are as given here. So, let us see. The first disk has a center of 0.5, which is the diagonal entry here. So, the diagonal entry is 0.5 and the radius is simply the sum of the absolute values of the off diagonal entries in that row, which is 0.2 plus this, which is simply equal to 0.4, which gives rise to this disk. Now let us make a few observations here. The radius of this disk is 0.5 and the center is 0.5 and the radius as we see here is equal to 0.4, meaning what is the maximum value at which this lies is 0.9. So, this is the farthest that the eigenvalue can lie from the origin. Okay. And similarly, the closest that it can lie to the origin is 0.1, meaning the eigenvalues associated with this particular disk satisfy this property. Now, let us look at the second disk. The second disk now it has a center at 0.6 and its radius is equal to 0.1 plus 0.2, which is simply 0.3. Again, the disk looks like this, as it easily follows that for this disk as well, we know that the absolute value of the eigenvalue is strictly less than 1. Now, let us look at the third disk. It is again centered at 0.5 and its radius is equal to 0.2, which is given by this small disk here. We see that this again satisfies the property that mod of lambda 3 is strictly less than 1. So, now the Kurz-Courant theorem actually gives a very nice graphical interpretation of where the eigenvalues lie, which can be very easy to interpret or comment, which can be used very easily to comment on the stability properties of the system. For example, we have already discussed before that if in a given system, if all of the eigenvalues have their absolute values strictly less than 1, then we already know that the system is convergent. It follows from the Kurz-Courant theorem that for every I belonging to 1 to n, 1 to 3, mod of lambda I is strictly less than 1. Now, since all of the eigenvalues of A are less than 1, A becomes a convergent matrix and eventually owing to that all of the states converge to 0. So, now we know how the eigenvalues associated with a system matrix can actually be used to comment on the stability properties of the matrix itself. In the next lecture, what we will do is we will talk a little bit more about some specific kind of matrices and we will see how their eigenvalues look like, and if we can we will try to make some more comments on the properties of their eigenvalues. Those class of matrices are non-negative matrices, which we will discuss in the next lecture. Thank you.